So the middle section I record typically because I've gotten the trial run with 8 a.m. and I'm not sleepy yet with noon. So 10 a.m. Here we are. Yes. So what I've done is essentially I have taken everyone's exam scores on my little sheet where I'm keeping track of my Orgo babies. And based on the exam scores in the first few P sets, I've kind of triaged you all into like how worried I am about my Orgo babies. And so the link to sign up for like the Calendly like slots is going to go out first to the students I'm most concerned about. Just because I like want to make sure they have resources and they are willing to like reach out and ask for help. Whereas like if you scored above 120 on your individual exam, you are going to be getting the sign up sheet last. I'm so sorry. I would still love to meet with you. Don't get me wrong. I would love to do the 10-minute meeting, but also these meetings are very kind of like quick to the point. So come with like, hi, I want to discuss these things. These are the pieces of advice I want to get. These are kind of the strategy I want to talk through. This is my current study plan. Can you tell me like what you would improve on this? Or like, this is how I'm studying reactions. Can you look at it? Like come with like a specific goal of what you're trying to get out. And I think on the Calendly, I'm also going to have a little thing, a notes section where you can like write a note if you want to like say, hey, this is what I want to discuss. But yeah, it's going to be a bit of a sprint. The 10-minute meetings are a lot. I'm normally very tired that week.
What are the tranches? Because like we can pick towards like on the exam,
What are the what?
like the exam tranches, like with different schools.
I don't feel like I should tell the tranches. The thing I will say, this section has the highest average of any section I've ever taught. There is no one in this section that I am concerned about. Everyone in this section, I think, is on track to get a B or higher. Yeah, like truly. So really good job on y'all. Like this is the highest section average I've ever had in my 5 years teaching it, and about 8 or 9 sections total. So you did that. The other thing is it's about halfway through the term. Like I know we're in week 4 of a 7-week course. So here in the next week or so, I'm going to be sitting out like a mid-semester kind of evaluation survey. And it's something that we take very seriously of like wanting to touch base with y'all and see how the course is going, what is working, what isn't working. There are some things that we might be able to change like going forward this summer. So one thing that we're actually going to ask about is help room. Like, would y'all prefer to move the morning help room hours to Friday? And like, then you have it kind of split out among days because several people have voiced that as being an option. And we really need like a consensus of people if we're going to do that and like book rooms and move TFs. So like, if that's not something that you want, vote no. But that's going to be one thing. We're going to have you evaluate TFs of like clarity and pacing and things. We're going to have you like give feedback about lecture, about help room. And then as a kind of incentive for y'all to do the survey, we are going to give an undisclosed small reward. Don't know exactly what it is. Last year it was we added a few points to everyone's exam 2 individual score. We're probably going to do that again. But Tim was like, let's not say exactly what it is and then decide later. So if 85% of the class gets it, you will get some undisclosed small reward. It could be like we add like 6 points or 3 percentage points to everyone's homework scores or something. But I think that would help fewer people. And so I'm going to push for y'all getting exam 2 points because exam 2 I think is just generally harder. But any questions about the meetings, logistics of like what's going to happen? Again, it's going to be sent out in batches on Friday and Saturday, and you're going to have like 12 hours for each batch, I think. The meetings will take place next Tuesday, Wednesday, and Thursday. And then I think the mid-semester evaluation will be due next Wednesday. Questions, comments, concerns, complaints, fun facts, sad opinions. It's the opposite of a fun fact, sad opinion. Okay, cool. Then we'll jump into things. So game plan for today. Lecture 6 is kind of weird because we have reactions, but we're not really looking at the reactions in the same way we looked at the reactions for lecture 3 or 5. So the big challenge for lecture 6 is this kind of meta like analysis of like which reaction do you do? So when Tim started at 11:30 a.m. of in the next few minutes, try out the GFP system, I said, no, we're going to do that in section. That's what's going to happen. So we're gonna build up to going over the GFP, and we're gonna spend the last like 30 to 40 minutes just doing some practice and kind of working things and going through common pitfalls. But in order to do the GFP, we do need to know kind of the basics of these reactions. All the reactions are a bit simpler than the reactions you've seen up until this point. So we're gonna kind of learn the basics about her, go through each one of these little families, and then we'll do GFP stuff. And so that's kind of the game plan for today. Sound okay? Great. Okay, let's jump into it. So SN2 reaction is a substitution reaction, and wouldn't you know, substitution reactions substitute. Typically, they're substituting one functional group for another functional group. The mechanism is lovely, little one step. This is the whole backside attack thing, and then you replace the leaving group here with the nucleophile here, substituted. Again, the mechanism is really easy. So we have some harder things that we have to consider with SN2. One is getting the correct product stereochemistry, and the other is figuring out which molecules are good candidates for SN2 reactions. So to first answer that stereochemistry question, we have this phrase inversion of stereochemistry. The first thing that you should think anytime you see SN2 or think about SN2 is inversion of stereochemistry. Can we do a call and response where I say SN2, you say inversion of stereochemistry? SN2. SN2. Cool. I'm going to, in like 10 minutes, just say an SN2 out of nowhere. And you better, they're just like little robots. Inversion of stereochemistry. Like if I'm talking, I say, if you're doing SN2 reaction, inversion of stereo, it needs to be this like automatic response. What it is if we look at the original molecule and it's a stereocenter, if we rank the priorities 1, 2, 3, 4 is going away from this, this is R. Our backside attack means that in our product, the nucleophile is over here. So if the nucleophile and the leaving group are both first priority, which is typically the case because the leaving group's like a bromine, this is like an oxygen or something. So it's typically going to be first priority. Here we do 1, 2, 3, and we are now S. So what we've done is we've inverted the stereochemistry. Now, again, it could be the case. Like, do you remember the problem set problem where you had something of like, oh, we were trying to make the R product, but instead we got the S product. What happened? And it was like, when you did the reaction, the priorities shifted. And so you didn't get the one that you expected. That could happen here. That is not on the problem set. It's never been on any exam for this class. And so if I was you, I would not worry about it. And every time I think of this reaction, I would just think SN2. Thank you. So it's something to, again, just be broadly aware of that it could not happen, but for the most part, it's going to happen. So yes, we're about to do this. Yeah. So if we were asked to write the mechanism, wow, we love doing easy things. You literally just do the attack of the sigma star CBR, kick off the BR, done. Mechanism. That's easy. But now, if we're attacking something that has a stereocenter, this is where it's going to be a little bit trickier, where we have to consider the product. So there are two ways that we can do it. So the first way is we draw our R group here, and we see our leaving group here is this way in the plane. And so if we do the backside attack of our SCH3, which is just SCH3 minus, then we could just draw here, our SCH3, approaching this way. Now, if we do it this way, what we're going to do is we're going to keep the wedges and dashes the same, CH3 and H. So you can, right from the back, keep the wedges and dashes the same. That's one option. And do you know how we can check whether or not we inverted the stereochemistry? Do the really easy skill that you are all now experts at because you took the first exam of 1, 2, 3. It's R. Over here we do 1, 2, 3. It's S. So we see that we have actually inverted it. Great. We love to see it. Also, Ryan, I just got the notification the order is ready. Great. Thank you. the context was, I was like, I can't leave this room. Will anyone go and pick up my pavement order? And Brian was very sweet. So thank you. Okay, the other way to do it is look at where the leaving group is and put your nucleophile exactly in the same spot. So now we're going to put the SCH3 down here. And if we do this route, we have to swap the dashes and wedges. So we are going to have the hydrogen on a wedge and the CH3 on a dash. And again, if we check our 1, 2, 3, it's clockwise, but it's opposite day, so it's S. Both of these are the same molecule, it's just a different way of writing it. And so just like we had two ways of doing the enantiomer, we could do the mirror image, or we could just swap the dashes and wedges. Here we have two ways of writing the SN2 product. We can either draw it coming in from the other side and then keep the wedges and dashes the same, or same spot, swap dashes and wedges. Use whichever one is more convenient for you. If you want to have both of them just as tools in your arsenal, great. So now take a minute for this one and try to think backwards on this reaction. So first of all, what here do you think was the nucleophile that attacked? CN. And so we want it to be like NaCN. So it's a kind of like CN minus equivalent, and we just write it in our like ion pair. And then it's going to be replacing some good leaving group. Let's just call that leaving group bromine. So I want you to draw the molecule with correct stereochemistry that came before. Yes. I mean, generally, like versatility is a virtue. Sure. Like I like thinking of it as like, yeah, how do you want me to do it? I'll do it either. But it's really like if you pick one and that's your method, it should work for most cases. Yeah. Like I can't think of a one where it's not to. But I've written out the two versions. How'd you do? Did you write one of those? There is no reason other than sleep deprivation. Thank you. Cool. This is fairly easy. Great. It'll get harder. So let's talk about the three factors affecting reactivity. So y'all spent like a long time in lecture talking about this. And like, to be very honest, you don't need to memorize all that stuff. You need to have a broad idea, and then you need to start being able to recognize things as you're doing practice. But we're not going to ask you to like rank the leaving group ability of the halogens. That's just not a question that we would ask. And if it was on the exam, I would include it in the review session right before. So if I were you, I would not worry about that. And know that the main factor affecting SN2 is steric hindrance. So this is the main one that we care about for deciding whether something's good, fair, or poor for SN2. Now, steric hindrance is essentially the idea that if you crowd the reactive site on a molecule, you're going to slow it down, and to the point of it virtually not really happening. So when you have a really open reactive site, like on a methyl alkyl halide, then super fast, great. But if you have a tertiary alkyl halide and the nucleophile is trying to do the backside attack here, she just fully won't have it. Like you'll get a 2% yield or something. Like, so as we get more substituted out our carbon, we get slower. That's generally the trend. Leaving group ability, again, this one's less important, but leaving group ability is like how readily will a chemical group leave? And it typically has to do with base strength. So weak or stable bases are good leaving groups. And so this chart can really be constructed by using pKa values. That's one of them. And then there are some orbital size things. Again, don't think too hard about this. Don't memorize the specific order. Know which things are generally good leaving groups, which things are generally bad leaving groups. That's about it. Cool. Last thing, nucleophilicity. Ooh. I'm gonna have a child that I'm gonna name for nucleophilicity, not just Felicity, nucleophilicity. So nucleophilicity, I actually think is an interesting kind of concept of like how readily something acts as a nucleophile. And it's both like thermodynamic and that you have to have a high energy donor, and it's kinetic in that like the reaction needs to actually take place. So like bulkiness affects nucleophilicity. And if you are a bulky nucleophile, you're not going to be a good nucleophile. You're gonna have a low nucleophilicity. But interestingly enough, bases, it doesn't matter about the kinetics. It's just, do you have a high energy donor and do you want to grab a proton? Like that's all it is. And that's maybe just a thing that like me 7 years into organic chemistry, I think is interesting. And y'all, you can just ignore it. But one thing to know about this for the trend is that this is in a polar protic solvent. Solvents. Other classes will do a lot more with solvent effects. I may have one question on the problem set about it. I think in the past 5 years, there's maybe been one question on an exam, very minor, that touched on solvent effects. And again, if there is one, I'll include it in the exam review. But for right now, I would say don't worry about solvent because we are largely not going to be doing it. Like we are going to assume everything's in a polar protic solvent, and so we can assume this, and then we're good. But the solvents, I think, just add a complication here where there's so much kind of information and you're having to make so many decisions that simplifying it is going to be best for y'all right now. Yes. Protic means it has a proton that it could give, and aprotic means it does not have a proton it could give. Yes, so polar protic, it's more like has a like something that could hydrogen bond, like this partial plus and this partial minus, where something that's aprotic would be like DMSO, which dimethyl sulfonyl, I think. So you don't have any really polarized bonds with hydrogen here. Like you have CH bonds, but those are pretty normal because it's like 2.2 versus 2.5 electronegativity. And so you don't have like a H with a partial positive. And that's the big thing here that we care about for the solvent effects when you start to think through them. But yeah. There's one key player that we need to talk about. Her name is tert-butoxide. And I don't have a great reason, but I refer to her as be gay do crime, because that's just kind of her vibe, in the sense that tert-butoxide is an alkoxide, and alkoxides are good nucleophiles, but she's bulky. And so she's going to go from being a good nucleophile all the way to being horrible nucleophile, really, really bad. And so, like, if you want a situation where you have a molecule that is still a strong base, because we said that that's not the kinetic stuff, but it's a poor nucleophile and it won't do like SN2, you use tert-butoxide. Kind of mischievous. She also has many aliases. She's KOTBU, she's like TOK. You could also have like NA for these. And I don't know, she just gives off like energy. I don't have a better way to talk about it. Just like know about her and know that she's going to be making moves and that she'll come back later. Any questions here on SN2 and my really scientific explanations? Is there a question? Well, we can do it together. SN2? Lovely. You are on the ball. Ding dong. Are there questions though about this reaction? Okay, moving on from SN2. Good, good. Okay, so you will notice her. She's a little bit uglier. Whereas this, pristine. This is, I just copied it from last year, how I did it. And we can really see my growth here. In that, here, I was using a lot of color for like headings. That's a lot. That's very busy. Whereas here, I'm like, okay, headings are black and underlined. And then also separation. The separation makes it so much easier to read. So this is worse. I just like I wanted to get sleep last night. And so I didn't finish these pages for the update. So these are the ones from last year. And you know, my B is other people's A. So I'm okay with this. Let's talk about the E2 reaction. So what we're gonna do is this is an elimination reaction. And the broad idea of an elimination reaction is you eliminate a functional group, she gets kicked off, and in the process, you make a double bond. Elimination. What happens is, do you remember one little nomenclature note, which I was gonna make a figure about? Do you remember how when we were doing section 5 things, we said, okay, we have a carbonyl, then we have the alpha position, then we have a beta position. And we talked about these moves of alpha protonation, alpha deprotonation. Well, there's a similar kind of nomenclature for alkyl halides, but it's more annoying. So here, the group is just the bromine, and we call this carbon the alpha carbon, and this carbon the beta carbon. I hate it. It's arbitrary and bad. But again, it's going to be helpful to use the words here. And so just be aware of that. So when we talk about the beta position for an alkyl halide, we're talking about her. Questions on that? Cool. So what we're going to do is we're going to find a beta hydrogen, a hydrogen at the beta position, and a base is going to come along, deprotonate it. The electrons are going to flow in and make a double bond here, and we kick off the leaving group. Again, a one-step reaction. We love to see it. The mechanism is fairly straightforward for this one. But just like for the reaction that we just did, where there's immediate association that should come to your mind, for E2, the immediate association is anti-periplanar orientation. So can we do our call and response where I say E2 and you say anti-periplanar orientation? So. So the first thing that you should think when you think of the E2 reaction is, wow, lots of different speeds, a lot of different tempi. Can we do like anti-periplanar orientation? Anti-periplanar orientation. Work. So E2. Good. We're going to come back to her. You have room for improvement. But let's break down what this crazy phrase is. So anti-periplanar, awful, gutted. But it's anti, which if you do your Newman production, here you see the leaving group and the hydrogen are anti to each other. They are exactly opposite. So that's the anti. And then periplanar means in the same plane. And so the 4 atoms that have to be in the same plane are the leaving group, the hydrogen, and then the 2 carbons are going to make the double bond. And so you can also kind of see like here, because like they're all like in a straight line, they're in a plane that's like going away from you in the Newman production. So like if you are anti, you must be periplanar. But if you were periplanar like this is just periplanar and it isn't anti. Does that make sense, or have I started speaking gibberish? Okay. This is the strongest section again in history. I guess I'll just go fast, please.
Wait, why would I understand how?
No, the R2 and R3 are not periplanar. They're not in the same plane. Like I'm saying, these 4 atoms need to be periplanar of this carbon, hydrogen, leaving group. Now, this diagram is something that if you go on to take Chem 27, you are going to see a lot of. So it's a really key idea that comes up a lot when you're talking about enzymes and where you're talking about like how enzymes set up reactions to happen. These electrons right here are going to be the ones that go and make this double bond, right? And we've broken this bond. And so if we've broken this carbon leaving group bond, then what does that mean? Where did our electrons go? The antibonding orbital. The call and response. It works. It's in there forever. So we broke a bond, we put electrons into the antibonding orbital, which is going to look like this. So when we have the antiperiplanar orientation, this antibonding orbital that's going to accept the electrons is right next to the sigma bond where the electrons are coming from. And so it's kind of like you're setting it up so that when the base comes along, she can just go whoop, and it breaks the bond all at once. And it's real quick. And yes, she disappeared, but that's why I'm trying to be like, it just happens. When you set it up, it's like setting it up for success, and then success happens, and success is a double bond in this case. But this idea is going to come back again a lot when you look at enzymes. And so I just want to kind of flag it here. And this is a result of that anti-paraplanar orientation. That's why we care about her. So for this reaction, we essentially have some options. So let's look at this molecule here. And I want you to tell me, how many beta hydrogens does this have? So on the left, we have 1, 2 beta hydrogens. So each one of these could hypothetically be our beta hydrogen that we rotate and make anti-periplanar and then do the whole thing. So we have options for which alkanes are going to form. Now, if we do form an alkene here with this right carbon, what we are going to make is an alkene that's in the end. It's terminal on the end, and so we call it a terminal alkene. Whereas here, if we make an alkene with the left one, we make an internal alkene because it's in the middle of the chain. Now, which do you think is going to be more favorable, a terminal or an internal alkene? Internal, but also like we haven't really given you reason to like know why. And to be very honest, I don't have a good explanation. The reason why internal are favored is because this Russian dude, Zaitsev, did some experiments and was like, they're more stable. And I said, thank you. And I didn't question it any further. So what he proved was more substituted alkanes are more stable. So the fewer hydrogens on there and the more alkyl groups, the more stable the alkene is. Now, when you have a terminal alkene, that means at least 2 on the alkene are hydrogens, right? Because it's not in the middle of a chain. So that means that you are like here or less stable. Whereas when you are internal, it means you have at most 2 hydrogens. So that means that you are going to be in this camp. And you can imagine like here, you could make an internal alkene that's fully substituted. That's just more stable than the terminal, hypothetically. So we're going to get more terminal than internal because of Zaitsev's rule. I think the actual exact numbers here are 25%. You don't need to memorize the percentages, but just know that there's more internal, and 55%. But then among the internal alkenes, we have the cis and the trans. Which do you think are going to be present in a greater percentage? Trans, yes. So why? Just why? I heard sterics and then something else here that I just couldn't make out, but I'm going to assume it was like sterics or sterics J-stat. Yeah, like if you have the big bulky groups, like imagine this was a tert-butyl, and this tert-butyl had hydrogens on it, and oh, there are hydrogens over here, they're going to start bumping into each other. They're going to be really upset. And so it's actually kind of weird because it's not necessarily always going to like follow with ease. Like easy, you could have like over here, this is connected to a nitrogen. So like this would be higher priority, this is higher priority, but it's about what's bulkier that chooses it. And so it's not something that I think you need to like stress out over, but just big things on opposite side make good alkene. Cool. So the kind of 2 like take home messages from all this like experimenting are 1, internal alkenes are favored more than terminal, and 2, among internal alkenes, trans are more stable than cis. The cis are very unstable. Work. Now, we can mess with this slightly. So, do you remember our good friend Bigay du Prime? So, Bigay du Prime is a bulky base. And with it being a bulkier base, it's still going to be a good base. Like, it's going to be a really strong base. It's going to do really great acid-base things. But instead of favoring the internal alkene, like you would do with like ethoxide, it's going to actually favor the terminal alkene, just because these hydrogens are a bit more accessible and it can go and like grab these from the outside. Whereas these hydrogens, you have like more steric bulk that you are trying to avoid. So if we want to mess with this rule of like internal or favored, we use a bulky base. We use BK du Crack. Cool. Now, the main factors that are affecting E2 reactivity are geometry, which is the anti-periplanar, which I abbreviate APP because it's just a mouthful, and basicity. So, like the whole thing, like this is really just a fancy acid-base reaction, right? So the better base that we have, the more likely this reaction is to happen. And this is where knowing your pKa charts and having those down cold is going to help you out. There are two typos. One is OH minus instead of just O minus floating in space. And the other one is this should be CN minus. Again, that's Pascal Colton's mistake. So blame him. Now we say that a strong base is OH minus or better. And so OH minus alkoxides, those are both strong bases. Carbanions, yeah, and nitrogen, and anions and alkyne anions, all good strong bases. Really, you're mostly just going to see these two. Then we say anything that's H2O or weaker as a base is a weak base. So water or alcohol. So this is kind of like a subtle point of like NaOET, good base. Strong nucleophile. But HOET, poor base. Bad nucleophile. And it's because of that charge. Like when we don't have the charge, we don't care about her as much. Like she's not going to be as reactive. She's not going to want to pull a hydrogen off as fast. She's not going to want to attack. So it's an important difference between alkoxides and alcohols. So alkoxides are good and alcohols are bad. And then we say anything whose base strength is between these two is going to be a fair base. The main ones to keep an eye out are NH3, cyanide, and acetate. But that's about her. And yes, we are a bit ahead of schedule. And so I did like a little impromptu. We're gonna go and like look at something. So is there any questions here before we go and look at this kind of interesting example? Any questions on the E2 reaction? Wow. Thank you. Thank you. Y'all are learning. Any questions on that or the SN2? Wow. I feel powerful. Thank you. So let's look at this interesting example. I'm going to go ahead and just tell you we're looking at E2. The kind of deciding why we'll like talk about later. But if we are doing E2 here, we know that we have to have that anti-periplanar orientation. Bye. So what I want you to do first is, because here it's hard to see anti-periplanar, like it's hard to see like an anti-orientation. I want you to draw both chairs of this molecule, which is a skill that you all can do after the exam. So take a second, write both chairs. So yours should look something roughly like this in terms of one of them two axial, one two equatorial. Which one that I've drawn, left or right, is more stable? Right, it's more stable. So now the next thing that I want you to do is I want you to identify the beta hydrogens and draw them on your chairs. So remember your alpha positions here. So your betas are here and here. In case you're curious, it keeps on going. Delta, or alpha, beta, gamma, delta, epsilon. So counterclockwise to the BR, we have H's here and here. And clockwise to it, we have it here. And then the same over here. We have here, here. And then we have here. Okay, so I want you to look at these four. Are these anti-periplanar to each other? No, she's sticking out to the right, like here, and then this is up. And so like if we did a little Newman projection, we would have like the H here and the BR here. So that's not anti. She's also not periplanar. Okay, let's look at her. Are any of the positions anti to this? If we look at the back, we have like a BR here, and then we have H. None of these are anti. Is this anti-periplanar, like this one? No. So what we have is, even though this right one is more stable, this is not E2 reactive. Because there's no anti-periplanar beta hydrogen. Interesting. Now, are there any beta hydrogens that are anti-periplanar on the left one? I saw a small nod. Yeah. It's gonna be this. So if we kind of draw our eye looking this way, we have BR going up and the H going down, and this is all in one plane. So this is the only option for like the conformation that the chair could be in first. And two, the specific hydrogen, which is going to make our orientation so that we can do the E2 reaction. So what we're going to have here is our base comes along, goes here, kicks up, kicks out. And then when we do that, we're going to have a double bond formed right here. So notably, like the other one that you might think could happen is you might think you could do this one as an option, right? Where you make a double bond here and then like have the methyl. And Zaitsev's rule would be like, that's correct, right? Like Zaitsev's rule says this is a more substituted alkene on the right. But she's just fully impossible. She's not an option. If you had this on a wedge, and then you had your like CH3 here, and then your H here, then now you have two options. You could go either way on the right. But this is kind of what you need to be considering when you are doing like E2 questions on a ring. So like this little aside is called E2 on a ring. And the other thing I want to say is here, even though this is the less stable conformation, this is the E2 reactive conformation. So the molecule is mostly going to be sitting in this chair structure. But then for the reaction to take place, it will sometimes go into this higher energy state. And when it will, it can react. And because of Le Chatelier's principle, that's going to drive things out of the reaction. So over time, we are going to have a forward reaction and get our product here. But this is all kind of subtle. And this is like half of the challenge problems. Like half of them are like E2 on a ring and like the intricacies of it and all the things that show up. And normally it's just like a surprise for y'all when you get to it. And I wanted to try to like head that off this year and like give y'all some info. Yeah.
Would their answer would both be with their-
Well, in that case, here, you would go Zaitsev's rule because both of them are options. And so you'd go with the more substituted alkene. Yeah, that's the major. And again, this would be a minor product, so it's still formed, but this is the, if we ask for the major. The other thing I will say about this is, I had a thing and it left me. Oh, The notable thing here is the E2 reactive conformation faces the leaving group axial. Because when you're equatorial, you're not going to have any of these neighbor positions be anti-periplanar. So the only way you can have anti-periplanar within a ring is when you're leaving groups axial. That's going to come up on the problem set, okay? Yay, impromptu little E2. Okay, let's talk about SN1E1. So I'm going to continue the trend with this lecture being very not scientific. And so the SN1E1 reaction, I have a little story. And it's like sometimes when you're in a relationship and you say, this is not working. And you say, I have to leave. And sometimes that's a positive thing for you. So the first step for SN1 and E1 is leaving group decides to leave, and it forms a carbocation. Can you say that word with me? Carbocation. If I catch any of you saying carbocation, I'm gonna lose my mind. I know carbocation sounds wrong, and carbocation, you're like location. Any other Asian sounds like fancier. It's carbocation, and if you say it the other way, I believe. Thank you. So I will be the leaving group. Thank you. And I don't think that'll be a positive experience for y'all. So when we have a carbocation, we have an empty p orbital, and from here we have some options. So option one is a nucleophile could just come in and attack, and we get a product that looks just like a substitution reaction, that looks just like SN2. So this one we call SN1, that goes through this different mechanism, and we do it because the rate limiting step here is unimolecular. Like the slow part of this reaction is the leaving group leaving. Whereas here for SN2, you have two molecules that are affecting the rate here. So it's bimolecular. So it's SN2 versus SN1. So this is a substitution product that goes through this carbocation aramida. And you can also have a beta hydrogen over here. Base comes along, deprotonates, folds in, makes an alkene, and you have an elimination, but through this carbocation unimolecular thing. And so this is an E1 product. So they look very similar to ones that we've seen before, but the way we got there was different. So that's the mechanism. She's not too crazy. The big thing that affects SN1 and E1 reactions is going to be carbocation stability. I was debating whether or not to do the Collin effect, the call response. That's it. I'm losing my mind. Let's do it. So the first thing that you should think when you see SN1E1 is carbocation stability. So SN1E1, SN2, E2, SN2, SN1E1. Cool. I love the participation. Thank you. Okay, great. You're doing well. It's my little Orgo robots. So let's talk about stabilizing the carbocation. We have to talk about this thing called hyperconjugation, which I'm also going to describe in very non-scientific ways. So I think about a carbocation is like you have a charge. There's a problem going on. And here, hyperconjugation is like a neighboring sigma CH bond. It's not one of the ones that's attached to the positive charge because that's like the family that's going through the issue. And it's like, there, I'm so sorry that the leaving group left. Are you okay? Where it's like a concerned neighbor, but it's not resonance. Resonance is like your ride or die. I will take on this charge with you. We will raise the other children together. We've got this. But this is like condolences. So this is stabilizing. Like if you didn't have the community of people being like, they're there, then this would be crazy reactive and like horrible. But it's not going to be nearly as good as resonance. So what we have here is when we have a methyl carbocation, we have no neighbors. We only have the family with the positive charge. And so she is least stable because 0 donors. But when we have a primary carbon, one that's connected to one other carbon, well, that carbon is going to have 3 of these sigma bonds that can be like, they're there. You've got this. And so this one's more stable. And then as we start adding carbons, we get more and more. And so by the time we're at tertiary, we have 9 neighbors being like, you got this, girl, go, pull through. It's much more stable. And so tertiary carbocations will exist, whereas methyl and primary carbocations will not exist. Again, I know that's not sciencey. It's really about like the overlap between the MT2PC and the sigma, and like it lowers the energy, but just very slightly. But like that to me is less effective than like telling all a story. And I think you remember the story. The other thing is on PSETs 2 and 3, you did see some examples where we talked about alkyl groups being donating, and we didn't really give you a reason. This is the reason. So it's this hyperconjugation where it just kind of leans the electrons closer, and it stabilizes a like partial positive charge. And here, this carbonyl, like normally this is a dipole. So we kind of snuck that in there. The other way I like to think about hyperconjugation, this is kind of like a big brain idea. So if it's confusing, don't worry. You know how induction is kind of like tugging electrons away from something, but it's not full resonance. It's not delocalizing them. Hyperconjugation is kind of just like the opposite of induction. If induction's tugging a little bit away, hyperconjugation is just leaning a little bit over. And so it's just kind of these subtle effects that do have real ramifications on reactivity and acidity and things like that. But it's just not as much as. Are there questions about hyperconjugation? Yeah. You should specifically use the word hyperconjugation now that we've introduced it. Up until this point, yeah, you just were kind of like, you told me. And now we're like, hyperconjugation. Also, when you use a word with that many syllables, you sound very smart. So now here we position tertiary carbocation as the most stable, but remember, resonance trumps everything else. So when we have a carbocation that's adjacent to a pi bond, an alkene, this has just straight up resonance. And so instead of having just like a stabilized partial positive charge, this atom really has like a third of a positive charge because we are spreading it out. So this is much more stable. And she has a special name. She's like Allie. She's an allylic cation. The position that's one away from an alkene, we call the allylic position. It's not something that we're going to test you on, but like, she's cool. Like the cool kids know about the allyl cations. I don't know why, but I think of her as like an influencer. Just like, oh, she's doing things. She's making moves. She's connected, truly. And then similarly, she has a cousin, the benzylic cation, where the position carbon right next to a benzene ring is called the benzylic position. And this has connections out the wazoo. This is like a Nepo baby. The best one of all, though, is when we are adjacent to something with a lone pair, because here, a resonance structure has a complete octet on all the atoms, whereas all the other ones don't have complete octets. So there are special cases that are going to be more stable than just a tertiary carbocation. Now, carbocation stability is the main thing for SN1E1, but we also have like 3 more facts that we want you to know as kind of like parting shots before we go on to the whole big shebang. So one is that SN1 reactions give a mixture of S and R, whereas SN2, exactly, you get inversion, you get one product. So it comes from the fact that we have an empty 2p orbital here, and our nucleophile could attack the empty p orbital from the top or the bottom. And if it attacks from the top, well, in this case, we would get the S enantiomer. If it attacks from the bottom, we would get the R. And so Tim was doing the whole thing about, well, the ion is going to be trapped by the solvent. It'll be kind of close, which is, yes, fine, good, dandy. The big thing that we care that you know about this is it's not going to be a 50-50 exact mixture. It's going to depend on the molecules in the situation, but you are going to have both. So SN1, you get both. Now, second fact, tiebreakers. So whenever you do SN1, or you're always going to have some E1. Whenever you do E1, you're always going to have some SN1. And it's because both of them proceed through the same carbocation intermediate. Now, between the two, generally speaking, SN1 is going to be the major product. And it's because it's just faster. Like it's faster for a random collision to like have the MTP orbital and the nucleophile bump into each other than it is for this sigma CH to line up with the empty p orbital, and we have that donation across, and then the base comes along and deprotonates it. Like that's just a little bit more work. And so SN1 is faster. If we want to make E1 have a greater percentage of product, then what we do is we do increase the temperature, and that will give us a little bit more E1 product. Now, if we want only E1 product, we have a like sneaky move. And I was going to do some branding with her. Like she's kind of like, remember the CCL3 was the reverse card in there. This is like the Yu-Gi-Oh trap card or something. Like this is like, we can pull it out of our pocket and get only E1. So this is for secondary and tertiary alcohols. If we add concentrated H2SO4, which again, I'm now revealing like how like basic and like stupid I think about chemistry. I say, oh, you conk it. Like, I don't know why that's how it stuck with me of like, oh yeah, you conk it and then you only get E1. But this conk just means concentrated H2SO4, like really strong H2SO4. You will only get E1 product, not SN. And it's because what happens is she is sulfuric acid. She's just going to protonate here, and then the leaving group leaves. And then at this point, sulfuric acid just will truly never act as a nucleophile. It is very content on its own. It does not want to attack things. It's fairly bulky. So it's not going to do a nucleophile at all. So we get no SN1. And even though it's a really weak base, the only thing it can do is act as a base. And so we get the E1 reaction happening. So that is how we control and get only E1. We conk it. So SN1, E1. Do better. SN2. Great. SN1, E1. E2. Ding dong. Thank you for tolerating this. I know it's annoying, but like, I think it's effective. We'll see. Pavlovian conditioning, it really works, I guess. So now we are going to kind of put all of these reactions in dialogue with each other and try to develop this system that will tell us which reaction is going to happen. Because all of these reactions happen with things that look very similar. They're typically like alkyl halides or some other leaving group. And then like, look at these reagents. These reagents look like very, very similar. They're all cousins, if not neighbors or the same. So we need to have a kind of like algorithm for going through each reaction and saying, hey, how do we like find the major product? It's kind of like, do you remember the priority rules that we did for EZ and RS? Where you just follow the rules, do it a step at a time, you'll get to the right answer. That's what this is. So let's talk about it. For SN2 reactions, I know I said inversion of stereochemistry is the main thing to remember, and it is. But the thing that controls what is going to make an SN2 good, fair, or poor candidate is sterics. So if the alkyl halide is a methyl halide or a primary halide, it's a good candidate for an SN2 reaction. If it's secondary, it's fair. And if it's tertiary, it's poor. The other thing that makes it poor is if the nucleophile is bulky, like our friend terbutoxide, BK-Dupron. So that is the main control for like what you're going to rank GFP for SN2. For E2 reactions, it's really about the base strength. So if the base is as strong as OH, it's going to be a good candidate. If it's H2O or weaker, it's going to be poor, in the middle, fair. And then for SN1, E1, it's carbocation stability. So if the halide is tertiary, and we would form a tertiary carbocation, or better, like if we have a resonance stabilized cation, then it's going to be good for SN1 and E1. Secondary, it's going to be fair, and then primary methyl, it's going to be poor. Now, this will like give you a system where you can do some good ranking. Like if we try this first one together, this is what I do every time. I would explicitly write these out, like SN2, E2, SN1, E1, and make it like, this is a form. I am like a health inspector going to this restaurant, and I'm going to be going through my checklist and give each one of these a grade, good, fair, or poor. So SN2, the thing I look for is sterics. So I look at my alkyl halide, it's primary. Primary means good for SN2. Moving on, E2. I go and look at the nucleophile and it's OMe minus, which is a strong base. Strong base is going to be a good candidate for E2. And then finally, for SN1E1, I say, oh, okay, that would form a primary carbocation. So that's a poor candidate for SN1E1. So now we already see there's an issue with our system because what happens if we have two goods? And so we have a few other like things that we need to do before we can really finish the system. So one, we need to do these quality assurance checks. One of them is the nucleophile vibe check. Double check that the nucleophile is something that can be a good nucleophile and isn't your B-gated prime trying to like mess things up. So like, is this a really good like nucleophile or just generally a good nucleophile? Yeah, so passes the vibe check. The other one is an E2 reality check. Is there even a beta hydrogen? If not, then E2 is impossible. So is there a beta hydrogen? Okay, passes both checks, quality assurance. Then we can finally decide who wins. And if we have a tie, we go with whichever reaction is kinetically faster. So SN2 is faster than E2 is faster than SN1 is faster than E1. And that is the order of like speed of these reactions broadly, all things like equal. There are some fine print points that I have here, but that will kind of get us to where we can get answers for everything. So in this case, the winner is going to be SN2. So what we do is we write our SN2 product where we've substituted our bromine for an OMe. Okay. So do you want to do one more together? I think we should do one more. Let's look at the next one. First thing I do, I look at the alkyl halide, it's primary. So for SN2, is it good for a pour? Good. Then we're going to do our nucleophile vibe check. Do we have a good nucleophile? No, we have terbutoxide causing trouble. So it goes straight from good to poor. That's why we have to do the vibe check. Otherwise, we would have missed that. It's a crucial part of the system. Okay, then E2. Is this a good, fair, poor base? It's a good base. That's the tricky thing with terbutoxide. Great base, horrible nucleophile. So good candidate. And then SN1E1, what kind of carbocation would form? Thank you. Thank you. Primary. So primary is good, fair, poor. Poor for carbocation stability. The primary is only 3 neighbors saying they're there. Tertiary is 9 neighbors saying they're there. So what's the winner? E2. So we have 4 carbons and we make a double bond. This is really just a practice thing. So what I'm going to do now is I'm going to turn it over and give y'all like 10 to 15-ish minutes to work, and then I'll circulate and like answer questions. And then we'll go over them together. Cool. Also, this is PSET pages 5 through 7. Yes. I think I put them out of order. I think I did page 6 and page 5 and then page 7. But I'm okay with that if you are. That's forever here. We are. If you have a specific question now, I know it seems like you've done all of them. Your name is Katie. Your name is Anthony. Your name is Alex. Naya, Katie. The 2 Katies are in the same section, which is, we'll live with it. Oh, yeah, and then on Friday, not, okay. 8 a.m. has Layla and Kayla, and it really throws me for a loop. Okay, also, location. Yeah. Lily. Suchi. Samira. Hashem. Jonas Brothers. Band. Jonas. John. Also, do you go by John or Jonathan? But Jonathan, the way you spell it doesn't have an H, and so are you Jon? Okay, I respect your choice in life. Yeah, yeah. I mean, there's some people that are Jonathan, who do, when they do the abbreviation JOHN, which that feels crazy. Yeah. But JON to me feels too short. What? I don't know. But some people are JOH. Like I grew up and the two Johns that I knew growing up were JOHs. So, no, that like really the vibe check is only, are you harsh? Yeah. First sitting behind Anthony. I need to see your face for a second. I know I did. Are you Michelle? Work. Okay, I'm gonna come back and put myself. Let's look. Oh. No. Angel. Work. I remembered it because you said pain. Work. Okay. Y'all, okay. You also always sit in that order. Y'all need to like mix it up on day, like swap the seats because I'm always like suited with the Anderson stuff. And like that isn't always the case. Jonas. Kate. I was gonna call you Alex as well. I'm sorry. I was gonna call you Alex. And I always want to call you Anthony, but you were Anthony. Katie. Kate. 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 It's gonna ruin the Zoom again. I'm gonna have to write it with chalk.